Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, in previous lecture, that is previous session, yesterday we discussed a lot about compiler design. Today also, continuing from our previous lecture, we are going to learn more and we are going to learn about lexical analysis. If you might have watched our previous lecture, you might have understood about the various analysis, but today we are going to go more deep, and in this very session we are going to discuss about lexical analysis, and hope in future also we would be discussing about more analysis. For this we have again with us in our studios Mr.Sarfaraz Masood. He is assistant professor in Department of Computer Engineering, Jamia Millia Islamia. So first of all, I would like to welcome our guest Mr. Sarfaraz Masood, and sir, continuing from the previous lecture, as we discussed about various analysis, I hope today we will be able to discuss and we'll able to cover lexical analysis.
Absolutely. The same would be my aim. First of all, good afternoon to all the listeners over here. Thanks once again for calling me for this session. In the yesterday's session, we talked about the various aspects of compiler design, starting from some brief history along with some mentioning about the language processing system, to be exact. We talked about the fact that compiler is just a component of the language processing system, in which we have components like a preprocessor, the compiler follows by that, then we have the assembler, and followed by the loader linker. The task of this entire system was categorized as taking the source program from the user and then generating the final machine code, the relocatable machine code. Then we specifically talked about the compiler as a unit. We talked about the various 6 phases that are there in the compiler. These 6 phases were the lexical analysis phase, the syntax analysis phase, the semantic analysis phase, followed by some intermediate code generation, along with some code optimization, and followed by the target code generation. These 6 phases we discussed were totally in touch with the units called symbol table and the error handler. So in today's lecture, we would like to emphasize on the topic of lexical analysis, and we'd also like to understand how this process of lexical analysis happens. We also discussed that this looked like to be an easy process, as it only has to scan and read the source program and generate the tokens from it. So we'll just try to understand slightly a bit more about this topic and have a better understanding about it. Just to point down the objectives of today's lecture, we have the followings as it, the basic concepts and something about definitely regular expression. This topic would not be complete if we don't understand something about regular expression, and so I have mentioned also something about automata. We would like to understand what does a scanner or a lexical analyzer actually do. Once again, slightly more details. How does it work actually? Formalizing, token definition, and recognition. Some brief introduction about finite automata concepts. Also, we would like to know about the lexical analyzer generator, the LEX. We would end up with some concluding remarks, and also something that we may look forward towards in the future lectures. Before beginning, I would deeply like to acknowledge the various sources from which some of the examples and definitely some images were used for the purpose of this lecture. Fine, so here we are. This initial of the slide, it helps us to understand the entire system, or the initial system of the compilation a bit more in details. Yesterday, if you remember, the design of the compiler was actually divided into 6 phases, and they looked like to be a serial kind of an approach, where we had the lexical analyzer, which was then simply followed by the parser or the syntax analyzer. But just by looking at that, it was not very evident how this functionality was actually happening. But here we can see that it's kind of an interleaved kind of a process that is happening. The lexical analyzer, it takes a source program, it generates a token, gives it to the parser, as well as we also see some attachments to the symbol table. The token given to the parser, then the parser acknowledges it by issuing a get next token command. By getting it, the lexical analyzer gets active again and tries to extract the next token. So we can understand this fact that this process of lexical analysis is not happening in one serial go. It's actually a kind of an interleaved process that is happening with the parser also. So if we had some assumption of this sorts in the last lecture, that the lexical analyzer might create a bag of tokens and then get them together and forward them to the parser, and this action may happen in some serial order, but this is not the case. If this would have been the case, some problems would actually occur. There would be some design issues catering to those. The design of the compiler was changed to something like this. So we generate a token, we extract a token, we give it to the parser, we give some entries to the symbol table as well, and then we wait for the next acknowledgement from the parser to generate a token. So it's an interleaved process, as I've been saying. So that's a major difference between what we understood in the last class and what we are getting it over here. So we know the basic aspects of the components. We know the lexical analyzer is here to extract tokens. It will be scanning the content. That is why it's also called the scanner. It will be reading the things character by character. We've also heard something about the parser in the previous lecture, and we knew about the fact that the parser is here to check the order of the tokens in which it is being received. The symbol table is actually a data structure that is acting as a database for keeping up the records of the tokens that are being received. And in the later stages, some more informations and attributes about these tokens would be extracted from this program, from the source code by other layers of the compiler. And those will also be stored in the corresponding locations at the symbol table. So just to draw some difference, or just to draw a kind of a line between a scanner and a parser, first of all, I would like to emphasize about the fact that why we are drawing this difference. The basic fact is that if you look at it on a more abstract way, then the task of the scanner and the parser, they look like to be something more similar. The scanner is trying to extract tokens, is trying to check actually the order in which the characters of the tokens are being received. It's more about the order in which the lexemes are being received. And the parser is actually also checking the order on a much more macro basis. It's checking the order of the tokens. So in both the cases, we do find this behavior that the scanner is checking the order in which the characters are being received, and the parser is checking the order in which the tokens are being received, and are more on a sentence basis. Then why don't at times this question arises that why don't we implement the scanner along with the parser itself if they have similar kind of a behavior? It's only the level at which they are working. The answer to this would be that there are some design issues again if you do it. If we break it into these two parts, the simplification of design is always an advantage that we get, along with the fact that the implementation of scanner is on a different technical background. It's actually implemented using some finite automata and regular expressions. There is some technical difference between the use as far as the construction of parser is concerned. The parser are normally implemented using the concepts of context-free grammar and push-down automaton. And it is not advisable to use a push-down automaton for the task of scanning. So it's better that we use a different concept, a lighter concept, the concept of regular expressions and finite automaton for implementing scanners. And it's better to keep the parser away on a different block and to maintain a push-down automata or implement a parser using those similar concepts. So as per those differences, it's advisable to have a scanner on as one separate block doing its whole lot of tasks, and parser on a separate parser as a separate entity working for its whole lot of tasks. So just to point down some differences between them on the basis of their tasks, the scanner actually scans the source program. It removes the blanks, the new line characters, and the comments and the tabs and all those that is not wanted by the compiler on the later on stages. It definitely identifies the tokens. It also creates the symbol table and starts populating the symbol table with the tokens that are being received. It inserts the token into the symbol table. It definitely generates the lexical errors. We would also like to know about the lexical errors and the kind of errors that are being generated by the lexical analyzer. And last but not the least, it also sends the token to the parser, because keeping those tokens with itself would not help it. So those will be passed on to the parser in the order, in the very order in which they are being received. And the parser, on the other hand, it performs the hierarchical analysis. That is the task of checking the order in which the tokens are being received. The actions are directed by the order of the tokens, that the hierarchy of the tokens. On getting a new token, definitely it will update the symbol table entries with various information that it can generate or extract. It generates a parse tree actually out of the source program that it has got in the form of tokens. Also identifies syntax errors or hierarchical errors and definitely reports them. And there are many other tasks that are also performed by the syntax analyzer. So we have discussed about this thing a brief while ago, that why the scanner and the parser have been separated. this division of lexical from the syntax analysis, it actually helps in simplifying the conceptual model of the compiler. From a software engineering perspective, this is actually highlighting the following properties. It's having high cohesion and low coupling. We all know that as far as the software engineering concept goes, two modules having high cohesion would always be preferred, and if they have low coupling, again they would be highly preferred. So this model of breaking up these two elements would actually lead to this property that is always beneficial. It also means a well specified parallel implementation of the blocks, and we can see in the previous slide where the two lexical and the syntax blocks were shown in the diagram. The implementation became quite much very parallel instead of the serial behavior that we assumed it to be in the first lecture. This division also helps in increasing the efficiency of the compiler in terms of the better I/O techniques to improve this process. Definitely, this is a very hard-working module of the compiler, because it has to work with the program that is there in the memory. It has to perform a lot number of I/O operations in order to extract those tokens from the source program. So it's a tedious process, and any efforts to improve its efficiency would actually lead to the efficiency improvement of the entire compiler process. This division also encourages the portability design, which is highly important under the current scenario that is going around nowadays, where the platforms are many and diverse. We know the example of Java being a platform independent environment. Some basic terms before moving ahead. Token, first of all, it's a sequence of characters having some meaning to the system. We have discussed it earlier as well, that any sequence of character that a system believes to have a meaning towards it would be considered as a token. It's a collection of a common set of strings. To give examples of the same, identifier is a token, number is a token, relational operator written as relop is also a token, etc. Then we have a pattern actually. This is the rule which actually generates or characterizes the set of strings for a token. The tokens are the sequence of characters, fair enough, but what is the rule that is generating or governing those that order in which those sequence of characters should come? So that is actually governed by the pattern of that token. Finally, we have something called the lexeme. This is the actual sequence of characters that matches with the known pattern and is classified by the token. So token is a kind of a name given to a set of strings, a group name actually, identifier or number. The pattern is the one that actually helps or tells us that this is the way the characters in the token should be there, or the name of the token should be there. Then lexeme is that actual sequence of characters that you actually find and you declare that, okay, fine, I've got a token with me. As an example, we can see in this table, the token can be ID or identifier in short. The sample lexeme can be sum, result, A, 1, 2, 3. And the informal description about the pattern, you can say it's the letter followed by letters and digits, any combination of that. However, in C we have a bit more defined approach towards identifier. Then we can have an identifier called num, acronym for numbers. Sample lexeme can be 0.123, it can be 0 or 5.43 e to the power 12. So it's any numeric constant actually. Then we can have a token called const, which we find as it is written as const, const, and this description or the pattern is also the same way, const, const. Similarly goes for while, which is actually a keyword again. The token is while, the sample lexeme is while, while, and the pattern has been described as it is. So it's pretty strict. For the keywords, it's actually a pretty strict pattern that we have to follow. But for relational operators, we've got a whole lot of options. We've got less than, less than equal to, or the equal to sign. We've got the greater than equal to sign, and so on. So the informal description of the pattern is also given to them. So if we find this pattern in our source program, we declare that yes, we have found a token of having this lexeme, and this was achieved by this very pattern. Then we also have literal, something like written within these two inverted code that we normally write in the printf of any language, let's say C, or C, not in C++, yes. In C we write it within the inverted codes. That is called a literal. So a token actually is classified with the help of a pattern, and the lexemes are actual values of which are highly critical. These are stored in the symbol table and also returned to the parser on its get next token request. Now about the errors. Now one thing very important to understand is because normally when we program, it's there within the logics that majority of the errors that we tend to make are normally from the syntax or the semantic background. So many times it happens that we are not having much of a knowledge about, let's say, lexical error, and we term any error coming out to be there in the compiler we say that this is a syntax error or this is semantic error, but no, there is also a concept of lexical errors that we tend to make, something like spelling mistakes that we normally make. So if a spelling that has been prescribed for a certain token or a lexeme has been prescribed, a pattern is there for a certain token, if not following that pattern, then in that case we are making a lexical error. So error handling is very restricted actually, but with respect to the input source. For example, the statement else if, you can see that this else if has been written together, there is no space between an else and an if, sum greater than 20 will not produce any lexical error whatsoever, because no spelling mistake has been done. You might be bothering that there should have been a space between an else and an if, but this is more towards a syntactical situation. This is more of a syntax error rather than being a lexical error, because if written together, then in the worst case this will be considered as an identifier. Else if can be considered as an identifier. So it's identified followed by parenthesis, followed by another identifier, followed by a relation operator, followed by a number, followed by a closing parenthesis. So it does not find, we do not find any kind of lexical errors being there in this statement. So we would rather not call it a lexical error. This may come out to be a syntax error in the later stages. So then when does a lexical error actually occur? It says that when the prefix of the remaining input does not match the pattern of any defined token. So let's say we have a pattern defined for a token and we are not following that while writing the word or the token actually in the sentence, then while doing that mistake actually we are doing the lexical error. For example, we all have been taught that the identifiers, the names of the identifier should always start with a letter, and in C we are also allowed to use the underscore for that. So if we take an example of the C language, then we can have an identifier by the name, let's say 2AB or no, sorry, not 2AB but 1ABC with this capital A1, X1, Y1, we can have such names, but the example that I took earlier actually were of those that cannot be taken as identifiers. For example, 2AB, it cannot be taken as an identifier because it starts with a number, and we have been told that it should not start with a number. So if the way a token should have been written, it's not being written according to that order or that pattern, then definitely we are making a lexical error, as the example being mentioned over here. The 2AB is actually a lexical error we are mentioning that I was actually talking about. Why? Because this cannot be a number, because this 2 is being followed by a character, so this cannot be a number, and this would be a problem for the system actually. By reading 2, it would not be able to come to know if this would have been a situation, let's say such numbers, such identifiers are also allowed. Then just by reading 2, the system would not have been able to understand whether it's about to get a number or it's about to get an identifier. It will always be a confusion till the point in later stages when it finds something else. So we cannot allow such a confusion to go on. So it's better that we have very strict rules about it. We said that you can have underscores, you can have letters in the beginning, but you cannot have numbers in the beginning. This can be followed by any combination of letter, underscore or numbers actually. So if this kind of a mistake we have done, it's a lexical error. In such cases, when a lexical error has occurred, then possible error recoveries are also there. So we have talked about this, that the compiler should not just stop at the first error it encounters. It should definitely try to recover from that error and move on. If it does not do this, then it will be a problem for us, and it will be pretty hectic task for us, that it does one error, it stops, we do it again, finds an error and stops. So in all these analysis phases, we try to find out, we try to have a design in such a way that the recovery of error is always possible. It finds a lexical error, it recovers from that, tries to recover from that, it identifies a syntax error, tries to recover from that, and so it happens from the semantic analysis phase. So the idea is that try to identify as many errors as many possible in one phase at least. So as far as lexical error recovery is concerned, you found that there is a character that should not have been there as per the pattern of a certain token. So let's say you were reading a number, and then you were there on the number machine, and then you found an alphabet there that you cannot find on that very pattern. So what is the possible thing? You have identified there's an error, no doubt there's an error. So how to recover from it? So one of the options is to try and delete or insert some input characters. You try and replace or transpose some characters if that might help. And if this even does not help, then you can simply skip over all the characters that you find unless you find a delimiter, a special symbol that marks the end of a token. So once you find that, you understand that, okay, fine, I have found a problem in one of the tokens, I have reached the end of that, and I'll start afresh. So you start with a fresh token identification process altogether. So you ignore the remaining the characters in that very token. Definitely efficiency is an important role player in lexical analysis. It will always be an important aspect. Why? Because this is a very, we say, crude kind of a phase where the analysis has to be done on the program, and that program has to be get into the memory, and then you have to interact. So a lot of I/O is actually required, and we all know that in systems the I/O operation tend to take quite a lot of time. So even in the process diagrams, we all understand that for I/O, our process, they move out of the league and they go into a wait state actually, or I/O state, and they are taken away from the processor. So they tend to take quite a lot of time. So it's always important that our I/O should be as efficient as possible. We've got 3 analyzer construction, lexical analyzer construction techniques. One is by the help of some analyzer generators, which are very much available out there. You might even be knowing the names. One is the Lex, and we have a better one nowadays as Flex. Not just the better one, it's the GNU version of it. Then we even have the option of hand coding the high level language in terms of some high level language. So we can code our own lexical analyzer using a high level language. In this, the I/O is actually facilitated by the language itself. Or we can also hand code the compilers in the lexical analyzers in the assembly language also. In this, we have to explicitly manage the I/O. So I/O is definitely an important aspect as far as the lexical analyzer is concerned. So if we are talking about the input-output operations, then 2 levels at which it can happen. It can happen at the character at a time level. That means we can have a character I/O. So we read one character at a time from the memory, or we can have a block or buffered I/O. We all understand that we've got to read quite a number of characters from the source program. At times our line of codes can be in some few thousand of line of code we can have in a program. So imagine the number of characters that might be. So I don't think character by character at a time would be a good idea as far as the I/O is concerned. So we go for the block or the buffered I/O, where we maintain a buffer in which we read a block of memory, and we get that program into the buffer, and from that buffer actually we perform the lexical analysis. So this tends to speed up our work of this scanning analysis. This method utilizes a block of memory. It stores data from the source program to a buffer block at a time. We actually maintain 2 blocks. Why? It would be evident in the example or the algorithm that we do a short while later. The reason it can be understood here itself actually. Let's say we are actually reading, we have got something from the memory into the first block, and the identifier actually has reached some part of the identifier has reached the end of the first block, and the remaining part of that identifier is out of that block actually. So if, let's say, would have been having only one block in this case, then this half of the identifier would have been in this block, and half of the identifier would come when this block would be refilled. So if you refill this block, then the previous content would get overwritten. So there will be some design issues, some serious design issues, and there will be problems in reading the tokens properly. So we maintain 2 blocks in which we perform analysis in one of the block, and we perform I/O in the other block. So even if our token actually lies in 2 parts in both the halves of the buffer, then even then it will not get vanished away, it will not get overwritten, because we're not overwriting both the blocks at the same time. We are scanning in one of the blocks and we are filling up the other block. So this helps us quite a lot in retaining those half kept tokens in both the sections and still moving on. So now we'd like to go for an algorithm actually that performs the buffered I/O. It's a very commonly known algorithm, the Sentinel algorithm. As you can see in the slide, this algorithm actually, it works on, again, the 2 buffer technique, where we maintain 2 buffers as shown over here. You can see this is the end of first half of the buffer, and this is the end of the second half of the buffer. And as an example, this another end of file buffer that you can see over here is actually mentioning the end of the file from where you were reading. So this algorithm is pretty simple. This algorithm is only controlling the movement of the pointers, the movement within the buffer. It is not telling you about how to recognize or how to come to a conclusion that a token has arrived. This is only talking about how to move within this buffer. So it says we've got two pointers. We maintain a beginning pointer that always points to the beginning part of a lexeme, and we have a forward pointer that points to the concluding or the ending part of the lexeme. So we say that we move initially both of them, they are at the same position. The beginning and the forward pointer are at the beginning of the forward, are at the beginning of the lexeme. And then at each step we move this forward pointer one step towards the right or one step towards the end of that buffer. And we try to check whether we have reached the end of the token or whether we have reached the end of the file. So the algorithm goes as it is. We say that forward is equal to forward plus 1. Once we have moved the forward in the forward direction, then we try to see whether we have reached the end of file or not. This EOF actually is common for for all these three terms: the end of file for the buffer, the end of file for the file. So if we have reached at the EOF, then we have to simply once again check whether this EOF belongs to the end of halves or it is something else. If it belongs to the end of half, then we have to do something that has been mentioned over here. If the forward has reached the end of first half, then you have to reload the second half. You can see we're not filling up the first half again. We have just finished up reading from the first half, and now we have reached the end of the first half. So it's better only to fill up the second half and keep the first half contents as it is, because it may be possible that some of the contents may be there in the first half, and some of the remaining contents of a token may be there in the second half. So you're reloading the first half and you're doing forward equal to forward plus 1. By that you come to the first position of the second half. If let's say you were there at the end of the second half, that's the next scenario, then in that case you reload the first half and your second half content will remain as it is. However, in this case your forward pointer should not be done plus 1, it should be taken to the start of the first half. So it's a simple process. We're just trying to maintain the forward pointers and trying to move around in the buffer. However, if your end of file that you have encountered was not because of these first half ending and the second half ending, it was something else, then this hints at us actually that this EOF was because of the end of file character that was there in the file, which marks the end of the content in the file. So because of this, you would come to know that this is the right time to end the lexical analysis. No more content is about to come. You have reached the end of the file. So you can see it's a simple process that tries to tell you how you have to move around. Just to add on something more onto it, if let's say you have reached your forward pointer, the element on which it points is actually a delimiter. At that point you understand that your token has been achieved, and all the contents right from the beginning pointer up till the forward pointer together, they form the lexeme of the token that you have got. So you keep your beginning pointer as it is still, and you keep on moving your forward pointers till the point you find a delimiter or any problem actually. So the moment let's say you found a delimiter, it means that your sequence of characters have ended properly and you have reached the end of the token that you were reading. So you pick up all the characters right from the beginning pointer up till the forward pointer, and that is your token, forwarded to the parser, forwarded to the symbol table. Because we are dealing with strings, so some terms that we should always understand. Strings have things like prefix, we can also associate suffix with them, we can have substring, we can have subsequence. Just to brief you about them, prefix is actually a sequence, it's actually a string or a set of strings actually that we achieve by removing 0 or more trailing characters from a string. So it's a string that we obtain by removing some trailing characters. For example, let's say that we have the string base. So if we remove some trailing characters, let's say we remove SE, then what we get is BA, so that becomes our prefix. Similarly, if we remove ASE, then we are left with this B only, and that is again our prefix. If we talk about general prefix, then we also have the case when we are removing nothing from the string at all. In that case, the entire string can also be called the prefix. Similarly, suffix is actually a string that is obtained by removing 0 or more leading characters from the string. So in the same case, we had BASE, we remove the B, that's a first leading character, we are left with ASE, that's a suffix for the string. If we remove BA, we are left with SE, that's again another suffix for this string. Similarly, if we don't remove anything from this, even then we are allowed to have a suffix that will be the entire string BASE. Similarly, we have a definition for substring. Substring is actually a string that is obtained by removing 0 or more prefix and or suffix. So if we try to remove prefix and or suffix together or separately, then the remaining content that we have in this case would be called the substring. So let's say we remove B, which was a valid prefix. We also remove E, which was also a valid suffix. The left over part is AS, that is a substring for a string. Similarly, we can derive this S, and also under the same definition we get base. However, subsequence does not talk about the continuity of the characters in a string. We can pick up any characters, but in the same order in which they are given in the string. So as you can see, we removed A from it. The leftover part is B, S, E, that is a subsequence. We remove B and S. What's left over is A, E, that is also a subsequence. And if we don't remove anything, even then we have something, and that allows it to be a subsequence, that is B, A, S, E base. However, if we talk about something different than this, that is proper prefix, suffix, or substring, then in that case we have an exception that we are not allowed to have the entire string as it is. So we cannot remove nothing from it. Okay, there's a concept of removing epsilon or not removing anything. So that is not allowed. So you have to remove something to obtain a proper prefix, proper suffix, and proper substring. Okay, so as we have been dealing with languages, so we just understand some concepts about language. A language L is simply a set or any set of strings over a fixed set of alphabets. So you define actually a set of alphabets that will be there in a language. So you have any set of strings over that can be classified as its language. For example, we have, let's say, two alphabets in the language 0 and 1. So in that case, the language set can carry a sentence as 0, it can be 1, it can be 0, 1, and so on, as you can see in the example. So as bigger sentences are also possible, like these 0, 0, 5 times followed by 1, or any combination that you can think about. If you increase the alphabets or change the alphabet, let's say A, B, C, then similarly we can have any combination, a set having a large combination of these alphabets. It can be as either simple A or B or C, or any combination A, B, B, C, or A, C, or C, A, anyhow. Similarly, we can talk about a range of numbers also. We can talk about range of alphabets also. It can be like capital A to capital Z. So in that case, the sentence is, because I have given a range of alphabets actually, so the language can contain these sentences also, like apple, bat, these strings also, cat, if, else, while, and so on. So it's a large collection of sentences or strings actually over a fixed set of alphabets that you define within that language domain. Then we talk about a regular expression, because the scanning task is normally done with the help of a regular expression and finite automaton. So a regular expression is actually a set of rules or techniques for generating a sequence of symbols known as strings from a given set of alphabets. So you can actually define a regular expression over a set of alphabets, which will help you in generating or governing the generation of the sequence of symbols known as the strings. Let this sigma be an alphabet and R be a regular expression, then LR is the language that is generated by the rules of R. For example, we have, let's say, a set L written as X, Y, Z. We also have a set, let's say, D given as 1, 2. Then we can have such languages as X or Y. We can have these other operations as well. I believe we have not done this cleans operator or the star operators as yet. So we would definitely like to go for a lecture on this part as well, because these concepts of regular expression and finite automata must be sound enough for people who are looking forward towards understanding this topic. Now we talk about more towards token definition. Regular definitions, actually they are associating names with a regular expression. So we have a regular expression and we try to associate a name to it. So together this forms or gives us something called a regular definition. So if we talk about the C language identifier, we can say something called letter. It is capital A to capital Z or small a to small z. Digit, it defines something like 0 to 9. And we also have something called use code, that's a short form for underscore I've used. By using these three, we can define something called ID or identifier, which is a letter or underscore followed by letter, underscore, and digits, any combination. This cleans closure or star operator that has been given over here, it refers to 0 or more or any combination of these. So by this definition, we can have an identifier by the name, let's say, one single underscore. We can have an identifier by the name underscore A. We can have an identifier by the name underscore 1, underscore, underscore, and so on. These are the shorthand notations that we normally use. The star operator is a clean closure that refers to the 0 or more symbol. Then we have something called the positive closure, that is the 1 or more representation. Then we have something represented as a question mark that refers to 0 or 1. These square brackets we normally use to represent the range of symbols or range of alphabets. For example, capital A to capital Z. All these things actually we use to define or to write regular expressions or regular definitions, because these are the ones that will be converted or later on changed into a lexical analyzer. So we must understand all these things, or we must have a knowledge about all these things. Just understanding the lexical analysis process is not going to help us in understanding its design. So informally, using the shorthand, we can see at the bottom that identifier has been written as something like this expression can be referred as to a regular definition, on which we have on the right hand side we have a regular expression, and together this is a regular definition for the identifiers. Then how does this token recognition actually takes place? This is actually a process that also moves around with your buffer or your pointer management. Actually, you keep on reading new characters from the forward pointer, and at the same time you also try to recognize that what character have you read, which machine actually it points to, which definition actually it meets. So we've got a whole set of definitions over here. We've got how identifiers are defined, we've got how numbers are defined, how we would see a while in our program, how we would see if, then, else. So all these regular expressions have been defined over here. So let's say I start reading the first character. I've read just the first character of my new token from the buffer. So that first character is actually going to help me in understanding that which of these machines should be picked up, which of these regular expressions should be picked up to be matched with. For example, I have read a number, that's 2. That's the first thing I've read. So as we can see in this, that all these definitions that have been proposed over here, they're all distinguishable by their first character. So if I read a number, I have no options whatsoever but to choose the number definition. So I would start comparing the remaining of my characters with this machine, with this regular expression. So the moment I come to its end, I'll understand. The moment I get a delimiter, I'll understand that yes, if everything was coming as per the number definition, so everything if was coming according to that, then I would keep on reading numbers, and the moment I get a delimiter, I'll understand that the number is over, the token I've got, and it should be passed on. Similarly, if I start with something like let's say greater than symbol, then greater than symbol is something that is not allowed in identifier, that is not allowed in numbers, that is not allowed in anywhere else, but only it's possible in something called a relation operation. So the moment I identify this less than, then I have another possibility that it can be followed by an equal to symbol. So if I have an equal to symbol, it's fine, it's less than equal to. If I don't have this equal to symbol and I have a delimiter, then I should be able to understand that this is something that I've received as a less than operator and will be passed on to the parser for the same thing. So the point to note over here is this, that my first new character of my first new token will tell me that which of these patterns is to be picked up, to be identified, or to be used for the later on communications. So if I have taken, if I've got a digit, then I'll start reading from numbers. If I've got an alphabet, I'll start reading from identifiers. But there's one simple point over here, that if I start reading, if I get a character and I start reading identifier, then identifiers would be confused with the keywords also, because they also start with normally they also start with letters. So as we can see, WHILE, while, IF, if, they're all starting with letters. So in that case, we just have to do one simple extra process. If the token that we have received, if its lexeme matches with a known keyword, then we keep it in terms of as a keyword, and if it does not match any known keyword of the language, then we simply read it as an identifier. So it's just a simple comparison that we need to do, and that will sort our matters. Other tasks of the lexical analyzer are to prune out the blanks, the tabs, the new lines. So we can define them in this regular definition. A blank can be defined as, let's say, B. I'm just denoting the symbol B because I need to represent a blank symbol. A tab, let's say, being represented by this T. A new line character, we all know it's represented by \n. So I can have a delimiter definition which says a blank or a tab or a new line, and then I can define something called white space. White space can be a positive closure of delimiter. That means one or more delimiters, if found together, will be considered as white space, and we have to remove white spaces. So in short, we are defining that the moment you recognize, obviously we have to recognize, we cannot say that we do not recognize blank. By the fact that I say that we will be removing or pruning out is only possible once we recognize them. So recognition of tabs and blanks and new line characters and comments is definitely important. So this definition helps us in recognizing them. So the moment you have recognized them, it's better that you prune them out. So you use this machine of white space. Once you've got this machine of white space working and you keep on getting those white spaces, you recognize them and you prune them out. You do not process them, you do not pass them on to the parser. So overall, we can look at this table and understand that what we have talked about till now. We do have a regular expression of white space, which is not considered as token. Whatever we get is not considered as token. They are recognized, but they are kept out, and they're not recognized as tokens. We do not have any attribute value for them. While is actually defined as while only because it's a keyword. No attribute value for it, no other faces for it actually. If, then, else, all are actually keywords, and they will be considered as separate keyword tokens by their own names. However, if we get an ID, then identifier actually, then the regular expression is actually only written as ID, but we should understand that this is actually pointing to the regular expression that we have talked about earlier regarding the identifier. So if we get something matching to this identifier regular expression, we treat it as our identifier, and actually we find its attribute value as pointed to the table entry. So goes with number, and so actually goes with the other things. So we have talked about regular expressions and lexical analysis, but actually finally we can see this thing happening. We can see this process of token extraction happening with the help of transition diagrams. Transition diagrams are used to represent tokens for the purpose of their extraction. As characters are read, the relevant transition diagrams are selected to attempt to match the incoming lexeme to a known pattern. So one should not be confused that we were talking about regular expression and now we are talking about transition diagrams. Students of automata theory or people who have already gone through this topic of automata theory must be knowing that every regular expression has its own corresponding transition diagram. So it's kind of a synonymous word we are using. So if you have a regular expression for a certain task, you can have its transition diagram as well. So we're just trying to change our way of looking at it. So each transition diagram has states, which is actually represented by circles. We're just trying to define how they look like. It also has transitions, definitely, which is shown by arrows between states. We have something called the initial state that actually points to the beginning of a pattern. We also have something called the final state that marks the end of the pattern. And each transition diagram that we're talking about is deterministic. Again, this is a term that should all be clear to the students of this field. There are two types of machines that we all know. One is the deterministic type and the other one is the non-deterministic type. We do have a couple of slides on that also. We'll talk about that in this lecture as well shortly. So in deterministic automaton, we know that there's no need to choose between two different actions. For each, at each state, for each input, we've got a very strict transition to take, and by that transition we move to one specific state, and so it happens for the later stages. So there's no confusion that at one state on one input we may be having confusion of like which state to move on. There's no such confusion. It's pretty much clear. That's why it's saying deterministic. So quickly looking at the examples of the deterministic transition diagrams. First of all, let's talk about the identifier. I've taken the example of, let's say, the C language identifier. So the moment you start, let's say, talk about any state number 9, 10 or 11, it's just a state numbering I've done. So if you get something called a letter or an underscore from the state 9, or actually any state, this state 9 is marking the beginning of a new token. So at the beginning of the token, if you have found a letter and an underscore, you should start moving on this machine, and you will remain in this machine until you keep on getting till the point you keep on getting letters, underscore or digits. So you have to be in this machine. That means your token is going on, the lexeme of your token is going on, and the moment you get something other than this, then you come to a conclusion that yes, my token is over. You can use this function simply to get this token to the symbol table. You can use this function actually to, now this is only a kind of a task that you have to make an entry of this into the symbol table and pass on to the parser. So this other actually is representing that you found something else than what you have mentioned. The other actually refers to not being a letter or an underscore or a digit. Similarly, for delimiter, we have defined delimiter already. It can be a white space, it can be a tab or a new line. So till the point, at this beginning point, let's say you are starting a new token actually, and the first character that you get is a delimiter. It is a white space or a tab or a new line character. Then you enter this machine and you keep on staying in this machine till the point you get a delimiter again and again and again. The moment you get something else, you move out of this machine and you understand that the list of delimiters that you were getting or the sequence of delimiters you were getting is now over. Similarly, for relation operators, we can use a better slide, this one. For relation operators, we can have a kind of a diagram like this. Again, the state 0 marks the initial state where, let's say, you are beginning, you are coming to a new point of reading a new token, and the first character that you read is actually a less than symbol. If that is the case, and it is followed by an equal to symbol, then we actually refer to the fact that yes, we have found a relation operator and this is less than equal to LE. So we're trying to say that at this return point that you have identified correctly a less than equal to symbol. If, let's say, this less than and greater than symbol together, they mark a not equal to sign, then this can be defined as it has been done. If on state 0 you get a less than symbol in your buffer, then you move to Q1, you move to the first state, one state. At this point you understand that you have received a less than symbol. If it is followed by a greater than symbol, it's something like you've got a not equal to operator. So you go and register into the symbol table, and you go and register it into the, you pass it on to the parser. If you've got something else, then it is only less than actually. So if you get something else, it says return relop LT. However, if you're not getting less than symbol, if you're getting equal to, then you simply you simply pass it on as a relation operator that is equal to. If you get in the initial part, if you get a greater than symbol and it is followed by an equal to symbol, you return greater than equal to. But if you only get a greater than symbol and is followed by something else that is not equal to, then the equal operator, then it is actually only the greater than symbol. So this is a very simple machine that is trying to tell you how you're going to understand, how you're going to recognize a token. So remember, this will be in conjunction with the algorithm that we have done. That algorithm was only talking about moving of the pointers, but this is telling you that if you, once you have moved on to a new position, read from there and see what is there on that space of the buffer. If that is matching, if it's any of these points, then you simply try to identify that token. And so we can design transition diagrams for unsigned numbers or signed numbers. You can see the last of the diagram, the simple one. If you get a digit and you keep on getting digits, it's a number, and the moment you get something else, it's actually the marking of the end of your number that you're receiving. So the upper ones are actually defining the numbers in more details. They can be signed, they can be exponential. So the idea is that the first character of your new token, actually, is trying to tell you that which machine should be picked up. Is it going to come on the identifier machine? Is it going to follow the number machine? Is it going to follow the relation operator machine? You pick up that machine and you keep on moving with that machine till the point you find something else. That something else should mark the end of your token, and this can be identified as a successful completion of one token recognition. We can just pose an example question. What would be the transition diagram for the strings containing each vowel in their strict lexicographical order? And the example answer is pretty much simple. We can say that the constants are A, E, I, O, U. So the strict lexicographical order is this only. So you can see this. The consonants are defined as B, C, D. All of them have been mentioned in the first definition, and then we can say this string, the question that you put up, this string is actually defined as this const star, that is any combination of consonants followed by vowels, followed by any combination of cons, followed by E, followed by this. And you can see in the diagram, this is much more clearer, that any combinations of consonants followed by A, then in the next state when you move, you have any combination of the consonants again, then E, then again any combinations, then I. So this would strictly give you a string that would be having any combinations of these consonants around these vowels. So this is what this question actually said. And if you have anything else other than these consonants and A or vowels actually, then this is nothing but the marking of an error. So this dead state is actually being represented just to show you that if you get anything else other than these two things, the valid things that have been marked over there, you should call it as an error. So the task of the lexical analyzer is also to differentiate between the keywords and the normal identifiers. This is actually simply done, as I discussed earlier, as I told you earlier. This is simply done by maintaining a simple list of the identifiers you have, and you associate some token values with it. So on finding that very string actually on the buffer, you simply try to match it with this list that you have. If it matches, on finding a match, the token is returned along with its symbolic value. In that case, let's say for example, then was the question. then will be associated with the associated value will be returned as 16. And if we do not find a match, the string that we have read from the buffer, if it does not match with the with any of these members of this list, then we simply assume it to be an identifier. That is, this is an identifier. So simple one step being added to discovery of a token or a keyword. Let's quickly brush up through finite automata and language theory, as I believe this knowledge is also necessary to complete this discussion about lexical analysis. Finite automata, it's actually a recognizer that takes an input string and determines whether it is a valid sentence of a language. That is the task of an automaton. It's actually a checker. It checks whether a sentence that is under question is a part of a language or not. This can be of two types. It can be deterministic, it can be non-deterministic. If it has more than one alternative actions for the same input symbol on a state, it's non-deterministic. On the same state, on the same input, I have two options or two paths to be taken, it's non-deterministic. However, if on each state at each input I've got only one path to be chosen, I have no alternative options whatsoever, then it's simply a deterministic automaton. So as the slide says, the deterministic automaton has at most one action for a given input symbol. Both these types of automaton actually can be used for the task of recognizing regular expressions, and they can actually be used for lexical analysis. However, the deterministic automaton are far more stable forms, and we normally tend to work in them. The non-deterministic finite automaton are easy to represent as far as regular expressions are concerned, but are somewhat less precise. And why it's saying, I have just discussed, because we don't have that much precision, that at least one of the state will have this kind of a precision loss, that at one state, one input, or one input, we've got two options to take. So we're not so much precise about the next paths to be chosen. Similarly, for deterministic finite automata, it's slightly more complex to represent the regular expression, but it offers far more precision. Just to show you an example of an NFA, as you can see over here, the diagram. On state 0, if I provide an A, it says I can come back, I can take a transition and come back to 0. However, at the same state 0, if I provide, if the symbol being read is A again, and I have another option of moving to the state 1. So this kind of a setup actually is referred to non-deterministic setup or non-deterministic automata, because at state 0, I am not able to determine whether on input A I should move to Q0, I should move to 0, or I should move to state 1. And a tabular representation of the same is shown below. That is marking a comma separated value in the state 0 under column A. So just a review about the deterministic counterpart of the automaton. As I said, it's a much more stable and an efficient way of representing your regular expression. Slightly complex, but the better way. DFA is an NFA with the following restriction, that for every state S belonging to this capital S, there is one and only one path from S for every input symbol A belonging to sigma. So in short, it means that at any state you can have at most one option available as a movement. So you can say on state A, if I have the next symbol to be read as 1, then I can only move to B. No such other option is available. On A, if I have an option of reading B, then I only have the possibility to move to C. So in the entire diagram, not even a single state is there that is creating any kind of confusion or non-determinism about the movement of the automaton. However, in state D, you can see that there is a transition to D on 0 and 1 both cases, but this is again not a case of non-determinism, because two symbols can take you back, can take you to the same state, but one symbol or one input symbol should not take you to more than one state. But that's the way, that's all the logic and the theory about it. How is the lexical analysis being developed nowadays? As we have discussed earlier, that there are three ways. One of them is by using tools, and the other two ways were actually by hand coding them in high level languages or the lower level languages. So if we choose the first option of using a tool, then we have a very well known utility known as LEX, which actually helps you to generate rapidly your own parsers with your own description. If you look quickly, then LEX program structure actually has three major components. The first part is declaration. Then we have these two % signs. They differentiate the declarations with the translation rules that we define, and this is followed by the auxiliary procedures that we need to follow. Slightly more detailed about it, the LEX tool actually takes input a LEX source program that is having the specification, the LEX specification. So that is fed to the LEX utility, which actually generates a C program, lex.yy.c. So the idea is you just give me the specification, you just give this LEX tool the regular expression, and what you want to do on that on the arrival of that expression or the completion of that expression. So this tool will actually convert your specification to a C program. So once you compile the C program, you will have if you're using the Unix environment, you will have this a.out file, and you can execute that. You give it an input, and it will give you the tokens. So it's like creating the compiler for you, creating the lexical analyzer actually for you. So you're not coding it personally, but you're just telling that this is the behavior you want in that. The behavior is described with the help of specification by writing the regular expression and the corresponding actions that are to be taken. And this tool is good enough and smart enough that it will create a C program for you, which can be simply used for further tasks. So you create a LEX file by the name, let's say for example test.lex, then the command lex.test.lex produces a file lex.yy.c, which is actually a C program. This program can be used as a scanner and will behave according to the specifications mentioned in. A detailed description about the way it's written, we'll simply go through an example quickly later on. First of these sections is actually some C declarations if you wish to have. Then the declarations that will be used within the specification. For example, if you have, let's say, some definitions for letter or digits or identifiers, then you have to have a section of rules actually that this is what you're looking forward towards being found out. And followed by those rules, you have to also tell the actions that if you get this, then you have to do this thing. And you can also tell some auxiliary functions that you prefer or you wish to be executed if at certain locations you want them to be. Quickly going through a simple LEX example, we have given some declarations. Let's say digit, it has been defined as a range from 0 to 9, letter being defined as a range from capital A to capital Z, small a to small z. And then we have given a local definition of int count. We're just trying to maintain a count as well. And then we are giving a regular expression. You can see the third part. Okay, this part we're giving a regular expression. We're trying to give a pattern that if letter followed by letter or digit full star, that's a clean closure. Then if you find out this pattern anywhere in the input, then you simply say count plus plus. So this is the expression that you want to find, and this is the counterpart. This is the action that you should do. So you're telling this to the system, and this will be ended with the main function where you're trying to execute this y/lex, which is actually a function call that starts this lexical analysis. And finally, you can print this value that you have. So this is a very simple LEX specification that is telling you that how you can find out the identifiers and what action. If let's say the count is the only action that you want to take, then how to maintain that count value. Another example can be viewed in similar terms. We're trying to specify something different. There you specified the white spaces. You've given the space, the \t and \n. And similarly you have defined. So it's on the similar lines as we have discussed earlier. So to conclude this lecture, we discussed lexical analysis process. We also talked about its efficiency issues. Definitely its efficiency is a big concern for the compiler. If this phase takes time, the entire compiler is going to suffer. For this we used the buffering techniques. We talked about the Sentinel algorithm. We talked about the two buffer techniques, two pointer techniques, where we take the beginning pointer and the forward pointer. We talked about the regular expressions and how we use it. And finally we concluded it with the LEX specification examples. In the upcoming lectures we would like to more talk about the next phase, that is the parsing. That is another very important phase of compiler design. So hopefully in the upcoming lectures we will be discussing about them.
Definitely, sir. We would be discussing about them in our future lectures. And thank you so very much for being with us and delivering such a productive lecture. Thank you, Mr. Masood. Thank you so very much.